Okay, now we are going for the microwave engineering. Okay, what is microwave? Little bit we'll understand. What is this microwave engineering, and whatever the basics we have studied, what is the prerequisite for this understanding of RF and microwave. Now here, if you will see, what is the major difference? Generally, the frequency range, what we are saying in the microwave is, this is 300 megahertz to 300 gigahertz is the frequency range for the microwave. Okay. Now the frequency range of the microwave is from 300 to 300 gigahertz. Now, by this frequency range, there are certain constraint, or there are certain things which are not like to the previous electrical engineering. There is certain differences in this. Now, what is that? So I'll just go for a waveform. Suppose you are going, this is what sinusoidal waveform. Okay, I'll just draw it, the sinusoidal waveform. Now this sinusoidal waveform, what it has, a positive half cycle and a negative half cycle. Okay, and this is what your axis, the vertical axis. Now it start with positive and negative. This is what your time scale T, and this is what your current, the I. Now what happened in this signal, that positive waveform and negative waveform. So here two parameters are important that we are going to discuss. One is the frequency and another is lambda is the wavelength. Now the important thing is, what is this lambda, that we need to understand. Frequency or the time period, they are inverse of each other. So from this point to this point, whatever the time period is there, that is the time of this complete cycle. This is a very basic funda, and this time period is inverse of frequency. So time equals to whatever, suppose I will take capital T is the time period, capital T equals to 1 by f. Okay, this frequency 1 by f. Now this capital T is 1 by f. This relation we are aware, so accordingly we can go for the frequency. Now I'll take some example of the frequency. Okay. Now in the frequency, if I'll take a frequency f1, f1 equals to the simple frequency, that is suppose 300 hertz. 300 hertz. This is what frequency I have taken. Now for 300 hertz, what will be the lambda? So I will need to calculate the lambda 1. What is this lambda?
So, sir, do we
Lambda
have
is
to
the wavelength.
calculate lambda 1 considering the speed of light or speed of
Yes.
microwave?
So speed of light is, we are considering in the free space, is equals to the speed of light. So lambda equals to,
Okay.
what will be the formula? C by
C by F.
C by F. This is the universal formula. So your C equals to 3 into 10 to the power 8 meter per second, and whatever the frequency, that is 300 hertz, means 300 per second. Okay, 300, as it is the inverse of time. Frequency is time unit is second, so frequency actual unit is per second, but in a glory of this scientist hertz, we given a name as hertz. So what is this lambda 1? It is a simple calculation. So 3,
10 to the power 6.
1, 3, 10 to the power 6. So 3 by 3, 1. So 1 into 10 to the power 6. 1 into 10 to the power 6. What is the unit? Lambda?
Meters.
Yes, because unit is meters. Here the C unit is meter per second and here per second. So per second will get cancelled, you will get the meter. So
Okay.
1 into 10 to the power. So this is what the unit balance. So this is what uh, 1 into 10 to the power 6. So this much is the meter. So may I say it is equals to 1 10 to the power 3 plus 10 to the power 3. So I'll put 3 0 1 2 and 3. And what is this? Instead of saying meter, may I say it is kilometer?
Yes, sir.
Okay, so this will be the kilometer. So I can write this as the kilometer unit. Now this is what my unit. Now 10,000 kilometer wavelength means what will happen actually? Can we physically understand what is this wavelength? Physical interpretation of this wavelength. So this is what the positive half cycle, this is negative half cycle. Okay. So what we are doing here, in the positive half cycle, this current is there. Means what? The current intensity is on the this axis, x-axis, and time is on the y-axis. Now current intensity initially it is zero, then it is increasing, then it is increasing, increasing, and at this it is the maximum. Then it is decreasing, 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 decreasing. Here it is zero. Then current intensity again increasing, 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 maximum, then decreasing, 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 zero. Actually what happened? Positive upcycle, current intensity is changing, that is from zero to maximum, and again maximum to zero, again zero to maximum, and maximum to zero. But why not this cycle, this negative half cycle is given on this side, positive side? Because the reason is the direction of current is this positive half cycle. If it is in this direction, so this current will be in the opposite direction. This current is in opposite direction. So what is happening here with reference to the lambda? So with reference to this lambda, here what is happening that what is your lambda? That is 500 kilometer. So what happened? 500 by 2, because it is divided into two part, positive half cycle and negative half cycle. So what happened? It is going forward how much? 1000 by 2, that is the 500 kilometer. This is wavelength is in kilometer. So you just imagine 500 kilometer it is going forward and 500 kilometer it is coming backward. Total wavelength is 1000 kilometer. This is what the simple interpretation of the wavelength. Okay, understood?
Yes,
So
sir.
500 kilometer it is going forward and 500 kilometer it is coming backward. So if you have put a cable of 500 kilometer, so if you will have, this is for what specific frequency? This is for this frequency. How much? Frequency equals to 300 hertz. If you will see the 300 hertz, then 500 kilometer it will go forward, 500 kilometer it will come back. But I'll take the another example. Same. That is another example of the frequency, different frequency. Now here frequency, I'll take the higher frequency. So higher frequency, I'll take here, suppose this 300 gigahertz, the microwave very high frequency. So if I'll put a 300 gigahertz, here the simple calculation, this is I'll say the F2. for f2 and lambda 2. So lambda 2 will be, again the formula is same here, c by f. So c by f, c remains same, that is 3 into 10 to the power 8. But this f1, instead of 300 hertz, it will be how much? 300 gigahertz. So 300 gigahertz means how much? I'll take, instead of 300, I'll take 30 gigahertz. Okay, so for the uh, better understanding. Okay, so I'll take the 30 gigahertz. 30 gigahertz. So gigahertz or 3 gigahertz is also okay. You can take anything. So 3 gigahertz. Gigahertz means what? It is 1 into 10 to the power how much? 9. So 1 into 10 to the power 9. So what will be the equation here? So here what you have to uh, put, that is 3 into 10 to the power 8. 3 into 10 to the power 8. This is what the frequency we are taken, and divided by uh, 3 gigahertz. 3 into 10 to the power 9. 10 to the power 9. What is the answer? Lambda 2 will be, so lambda
Point
2
one.
0.1, and unit will be meter. 0.1 meter. Okay, so zero point 0.1. Now where is this 10,000 kilometer, and here is his 0.1 meter? So what happened here? Again the same waveform. Now lambda 2 is here, zero point 0.1 meter. So here 0.1 meter means 0.05 meter. 0.05 means how much centimeter? 5 centimeter.
5 centimeter.
Uh,
5 centimeter.
so this for 300 gigahertz. So this lambda 2 I can tell in terms of 10 centimeter. So whatever your small scale, 10 centimeter. If you will see, compare your small scale which you are using in your compost box, it is 15 centimeter. So length you can
Yes.
compare. So this is 10 centimeters. So what happened here? So only 5 centimeter. Okay. So what happened? It will go 5 centimeter. 5 centimeter. It will go forward, and 5 centimeter it will come back. So this 5 centimeter is the major part. Now you can compare for the lower frequency like 300 megahertz, 300 hertz this here, and this 5. So here 5 centimeter it goes forward, and 5 centimeter it come back. Now if you will see this, if this is 300, this is 3 gigahertz, we have considered this 3 gigahertz. If you will consider 30 gigahertz, then 1 point it will increase, so it will be zero point 0.5 centimeter. If I will take f3, f3 equals to 30 gigahertz, 30 gigahertz. Okay, so what will be the my lambda 3? So lambda 3, it will be simple, you can put 1, so it will be 1 centimeter. 10 you can do. So this is 1 centimeter, means zero point 0.5 centimeter it will go forward, and zero point 0.5 centimeter it will reverse. So you just imagine this 0.5 centimeter for the higher frequency of this. Now here, if you want to calculate the uh, voltage, so voltage calculation, generally how we do? We do it from the voltmeter.
Hello.
So we require for the voltmeter or multimeter, you can say you require a cable. Okay, you require a cable. So you can put a cable and measure the voltage. If your wavelength is 500 kilometer, then there is no question, no problem. But if my wavelength is 1 centimeter, so in 1 centimeter, what is happening? 1 centimeter, you will have a complete positive waveform, negative waveform. This is happening completely in 1 centimeter. If my frequency I am considering the 30 gigahertz. So 1 centimeter forward, 1 centimeter complete waveform. So zero point 0.5 centimeter here and zero point 0.5 centimeter here. So what is happening with this? What is the reason that you cannot measure the voltage? Okay, so you cannot measure the voltage. This is what the greatest, what uh, you can say a problem with this, or the whatever the disadvantage or whatever you say. So with this, now the question here is that if this is what your waveform, and the two cases we have, the lambda, first case lambda 1 is 1000 kilometer, 1000 kilometer, and second case maybe for the higher frequency, this lambda 1 it represent for the frequency f1 of how much, 300, 300 hertz, and this lambda 2 it is representing the frequency. If we take f2 equals to 30 gigahertz, if this is 30 gigahertz, then it will be 1 centimeter. So this is very small wavelength. Okay, so here the question arises here, what is the, why we are discussing these two examples? So these two example we are discussing because here the voltage measurement, if you will measure this voltage, the lead will be more than 1 centimeter, because if you will multimeter or anything, so it lead is more than 1 centimeter. So in the 1 centimeter length, you will have this positive half cycle and negative half cycle. So completely. So it is quite difficult to measure the wavelength. But this is to measure the voltage. But this is or the current, because on the x-axis you may have the current or may have the voltage waveform, and this is your time waveform. Or you can have the time waveform or the so this is voltage and current. But if you want to measure a voltage or the current, so it will be the very difficult. So here for the microwave, we cannot measure the voltage and current. So what is happening here in the micro engineering? So in the micro engineering, we will come back to the two-port network. So two-port network mechanism. Here, as if you have studied ABCD network, the H two-port network, the Y two-port network, and all this thing. So here in the micro engineering, we are requiring the S parameter, that is the scattering parameter. So this scattering parameter, what basic or why we require. So this is the port number 1. So this is what you can say the incident port, and this is what the port number 2, or you can say this is the output port, input port and output port. So whatever the waveform is incident here, and how much is reflected from this port. Okay, so it is taken in terms of the incident waveform and the reflected waveform. And this waveform, what parameter, as voltage is difficult to measure, so we are taking the power. So how much power is incident on this port and how much power is reflected from this port. So why this is required, incident and reflected? Because if you will go back to your very fundamental, then there is a what concept. What is that concept? If you will have a very simple circuit, suppose this is what my generator. Okay, so my source is there, and this source has some impedance. Okay, this source has this some impedance, that is, I'll name this as the ZS, source impedance. and you are sending it to some load. Okay, load is where you are required to send it, or this is, I'll call this as the ZL. This is my source. You can name this as the V0 or whatever the source, whatever the power is there. So here maximum power transfer theorem, what it says, the ZS, whatever the ZS, whatever here ZS, it must be the complex conjugate of ZL, complex conjugate star. Now what is this complex conjugate? Means if your ZS is impedance. Impedance is represented in terms of resistance, maybe your RS, and reactance. So reactance is represented as JX. So JXS I will represent as it is representing the ZS. And the another is ZL. So ZL, the resistance reference to this, that will be the RL, and the impedance will be, the reactance will be JXL. Complex conjugate means whatever the imaginary part here, if this imaginary part is positive Jx, then this imaginary part is negative here, this is minus Jxl. And this is nothing but the maximum power transfer theorem. Maximum power will transfer at what condition? When this condition fulfills. And this condition may not be necessarily required to fulfill at the low frequencies, because at low frequencies wavelength is very low. As the wavelength is very low, so there is no question of the very short wavelength. But if you will have the narrow wavelength, these questions come. So in the microwave engineering, generally we are more cautious about this maximum power transfer theorem, and whatever the antenna or whatever the circuit you are designing, they are tuned to each other, because to transfer a maximum power. Suppose you are design an antenna, so whatever the antenna impedance, it should be matched with the source or whatever the previous circuitry. So input impedance of antenna should be matched with that. So there should be the matching, and this matching will give you the impedance matching techniques. So there are various impedance matching technique in microwave, and these impedance matching techniques are required, because it is not required at low frequency. At 300 hertz you don't require any impedance matching. So these impedance matching techniques are required at the lower frequencies. So this is what you can say a different uh, what or different phenomena for the microengineering, which is different from the whatever your basic circuits, that is the electric circuits. So here there is this microwave frequency is different than the normal whatever the frequency operation, and there we have to uh, what we have to deal differently. So there are all the devices will be different. Although the diodes are there working for low frequency, but diodes working at the high frequency are designed differently. Transistors at high frequency or micro frequency are designed differently. Passive devices, that is, it is called the microwave bench. If you want to transmit a microwave signal, so it cannot be transmit from the twisted wire cable, because the losses will be very high. The impedance matching comes into the picture. So either you can use the waveguide or a coaxial cable. Again, impedance matching is required there. So to transmit from the your source to the load, or your whatever the transmitting systems are there. So here examples will be your radars are there, satellite systems are there. So these many the example. The other examples are also there. So there you require a different setup. So that's why this subject is totally different, and it is dealing differently than the other subject.